Hello, and welcome to Differential Equations. This is lecture 23, Systems of ODEs. Last time, we finished our quick overview of linear algebra. This time, we're getting back to ordinary differential equations. So, of course, the idea is that now that we have some tools from linear algebra, we will use them to study systems of ordinary differential equations. Specifically, linear systems of equations. Okay, so systems of ordinary differential equations show up whenever you have coupled quantities. So for example, suppose we have a mass spring system with two masses and three springs. As follows. So suppose we have a wall and then another wall. And so here we have our first mass. Here we have our second mass. And they're connected to the walls and to each other by masses, by springs. This one was spring constant K1, K2, K3. And here we'll have the displacement from equilibrium, x1 and x2. And let's say that we also have external force F1 acting on M1 and external force F2 acting on M2. Right? The coordinates x1 and x2 would then satisfy the equations. Okay, so just using Newton's law, we have mass 1 times the acceleration, so the second derivative of x1 with respect to t. It's going to be, okay, so K2 times the compression of the second spring. So that's going to be x2 minus x1, right? And then, of course, K1, this first spring is pulling this first mass towards equilibrium to by however much it's displaced. And then, of course, we have our exterior force, F1. So we could group this together as the things that are affecting K1, sorry, X1, things that are affecting x2 and then the external force, right? And then we have the same story for the position of the second mass, but now we have minus k3 x2 minus k2 x2 minus x1 plus f2 of t. And so this would be k2 x1 minus k2 plus k3 times x2 plus f2 of t, right? So now that we're accustomed to using vectors and matrices, we can write this in terms of the vectors x bar, right, which is a function of t. This is the vector valued function with first coordinate x1 of t, second coordinate x2 of t, right? And then a force function in the form of a vector with first coordinate f1 of t, second coordinate f2 of t. Okay. So in terms of these vectors, we have dx bar with respect to t is equal to the matrix minus k1, k2 plus k2, then k2, and then k2, and then minus k2 plus k3 times the vector x plus the vector f, right? Or more succinctly, this is dx dt equals capital A times x bar plus f bar, where capital A is this matrix. Okay, so notice that this system of two ordinary differential equations can be written as a single equation for the vector valued functions x of t with forcing term f of t, also vector valued, right? So let me write that down. A first order linear equation for a vector valued function y bar is an equation of the form dy bar dt is equal to a matrix A, which can depend on t times y bar plus a forcing term f bar, which also depends on t. If this forcing term is identically zero, then the equation is said to be homogeneous, right? Just like when we had scalar valued functions. Otherwise, non-homogeneous or inhomogeneous. Okay, let's see another example where we end up with a linear system of equations. Suppose we have two tanks containing pure water. So let's say that we have, here we have tank A. And here we have tank B. Right, and let's say that tank A to start with contains 100 gallons, and tank B to start with contains 300 gallons. Right, so now let's say that each minute 7 gallons of water salt solution containing 1 pound per 1 pound of salt, 1 pound per gallon of salt is added to tank A, right? So here we have some spout, and we have 7 gallons per minute with 1 pound of salt per gallon. At the same time, 7 gallons of the mix in tank B is drained out. So here we have a little spout coming out, and we have 7 gallons per minute. In addition, the two tanks are connected by 2 pipes, right? So we have 1 pipe connecting here, 1 pipe connecting here. With one pumping water from tank A to tank B at a rate of 10 gallons per minute. And the other pumping from tank B to tank A at a rate of 3 gallons per minute. So we can ask how much salt is in each tank at time t. Okay, so let's let S sub A and S sub B be the amount of salt in each tank. So note that the total amount of water in each tank is constant, right? Because for tank A, you have 7 gallons coming in from here and 3 gallons coming in from there, and then 10 going out. And tank B, you have 3 going out, 10 going in, and 7 going out. Also, since we were told that we started with pure water, SA at time 0 and SB at time 0 are both equal to 0. Now, staring at the picture, we see that the change in SA is 7 gallons per minute of water times 1 pound of salt per gallon, plus 3 coming in from tank B. So that's 3 gallons per minute of water. And how much salt? Well, it depends on how much salt there is in tank B divided by how much water there is in tank B, 300, minus 10 gallons per minute of water leaving tank A. And there, the amount of salt would be the amount of salt in tank A. So salt A divided by 100. And similarly, the change in the amount of salt in tank B, we have 10 gallons per minute flowing to tank A, so flowing from tank A, so that's 10 gallons per minute times S of A divided by 100, minus 3 gallons per minute SB divided by 300, and then finally minus 7 gallons per minute times SB divided by 300. Okay, so we get these equations from the picture, and we can rewrite them SA prime of t is equal to 7 plus 1 over 100 SB minus 1 over 10 SA, and SB prime of t is equal to 1 over 10 SA minus 1 over 100 SB minus 7 over 300 SB. So if, say, capital S bar of t is the vector with coordinates SA of t, SB of t, then what we have is that S bar prime of t is equal to the matrix minus 110, 110, 1 over 100, and minus 1 over 100, minus 7 over 300 times S bar of t plus the vector S7, 0. Okay, so again, we have a linear system, a linear first order equation for vector valued functions where we have non-homogeneous because of this vector 7, 0. Okay, let's do a nonlinear example. Foxes and rabbits. So this is a very common model for population dynamics. Suppose an island is inhabited by foxes and rabbits. the foxes eat rabbits, and the rabbits eat plants. Assume that there are so many plants that the rabbits always have plenty to eat. Okay, so then what's going to happen, right, is we're going to have, say, the rabbit population is going to end up oscillating with the fox population oscillating similarly, but with some sort of delay. So whenever there are many rabbits, then the number of foxes increases until they eat so many rabbits that there aren't enough rabbits to sustain the fox population. And so it starts decreasing, which allows the rabbit population to grow again. And so the cycle continues. Right, so let's model this. Let R of t be equal to the number of rabbits at time t. And f of t be equal to the number of foxes at time t. If there were no foxes, we might expect that the change in the rabbit population would just be proportional to the number of rabbits at a given time, so some constant of proportionality. It's natural to assume that the number of encounters per unit time between rabbits and foxes is proportional to the product of the number of rabbits and the number of foxes. And to assume that a certain proportion of these encounters results in the rabbit being eaten. So we model the rabbit population with dr dt equal to a times r minus b times r times f, with a and b positive. Similarly, to model the fox population, we assume that the more foxes there are, the more they compete for rabbits, and so the fewer foxes we'll have. Also, that the more encounters there are between foxes and rabbits, the more foxes we'll have. So we model the fox population with df dt equal to minus c times f plus d times r times f with c and d positive constants, we therefore have the system of equations dr dt equals a, or let's say r times ar minus bf, and df dt is equal to minus f times c minus the cr, sorry, this was just a, c minus dr. Right, so this is our system of equations modeling the rabbit and fox populations, and this is a nonlinear system of equations, right? It is not of the form dv by dt equals a times v plus f. Right? So you can form the vector with r of t, f of t, right? But this right-hand side is not of the form matrix times that vector, right? So this is a nonlinear system of equations. Okay, one more example. This one is going to be linear. This is a procedure called order reduction. So let's start by considering the case of second order. Suppose we have a second order linear equation. Linear ordinary differential equation, such as the damped mass spring equation, right? M times x double prime plus gamma x prime plus k times x equals 0. Right? If we introduce the velocity, let's call it y, as a separate dependent variable, then x prime is equal to y, and the damped mass spring equation becomes my prime plus gamma y plus kx equal to 0. Together, these give us the system x prime equals y, and y prime equals minus k over mx minus gamma over my, right, which we can write using vector matrix multiplication as the vector x prime y prime equals the product of the matrix with first column 0 minus k over m, and second column 1 minus gamma over m times the vector with entries x, y. Right, so we've gone from one second order linear equation to two first order equations, which we can rewrite as one first order equation for vector valued functions. Similarly, if we have a third order linear ODE, say x triple prime plus a2x prime plus a1, sorry, that's a2x double prime, a1x prime, a0x equals f. Then we can introduce y to be the x prime, z to be y prime, so that's x double prime. And then z prime would be x triple prime, right? Which from here we can solve as f minus a2x double prime minus a1x prime minus a naught x. Right, and so we can replace the third order linear equation with three first order equations. Right, so x prime equals y, y prime equals z, and z prime equals f minus a2 y minus a1, no, sorry, a1, a2 z minus a1 y minus a naught x, right? Or in matrix vector form, we have the vector x prime, y prime, z prime, and it's given by multiplication of the matrix 0, 0 minus a1, 8 a naught, 1, 0 minus a1, 0, 1 minus a2, times the vector x, y, z, plus the forcing term, which is only affecting the final coordinate. Right? And you can keep doing this. Similarly, if you have an nth order linear equation, then you can replace that with n first order equations. So a system of n equations, each of them first order, or using vector valued functions, a single vector valued first order equation. There are many reasons why this is a useful thing to do, especially when you're doing numerical methods. It's much better to have a first order equation than to have an nth order equation. And it's okay if that first order equation involves vector valued functions. That doesn't make that big a difference. In fact, let me point out that the existence and uniqueness theorems that we covered previously continue to hold when working with vector valued functions. Right? So first, suppose you have dy bar dt is equal to some function f bar of y bar t, right? So this is the general case where there's no reason for it to be linear. This includes nonlinear. And let's set up the initial value problem. So you have y bar at time t naught is equal to y naught bar. So the theorem is just like before. We have local existence. If the function f is continuous in a neighborhood of y naught bar t naught, and local uniqueness if we also have that all of the coordinates of the function f and all of their partial derivatives are continuous in a neighborhood of y naught t naught. Right? Also, as before, this simplifies greatly if the equation you're looking at is linear. Right? So suppose we have a linear initial value problem. Then here the theorem says that if a of t and f bar of t are continuous functions of t in some interval, containing t naught, then there is a unique solution on this interval. Okay, so next, suppose v bar is a vector valued function of size n times 1, and that it satisfies the homogeneous linear equation dv dt is equal to a of t times v. Okay, so this homogeneous linear equation satisfies the superposition principle, just like the previous linear equations we were studying, right? Remember, that means that if you have two solutions, then the sum of those solutions is also a solution. And that if you have any solution, you can multiply by any constant, and that's still a solution. Right? Now we have vector valued functions, so we expect to have n sufficiently different solutions in order to get the general solution, right? And remember, sufficiently different, we found, meant linearly independent. So we're particularly interested in linearly independent sets containing n solutions. Right? So our vectors have n coordinates. We want n sufficiently different solutions, meaning linearly independent. And if you have a set of such solutions, then it is called a fundamental set of solutions. It follows from the existence and uniqueness theorem that every solution of the ordinary differential equation is a linear combination of this set. So that's why we call it a fundamental set, because you get every solution by just multiplying these functions by coefficients and then adding them together. A fundamental solution matrix for this equation is a matrix capital M of T whose columns make up a fundamental set of solutions. Right, so that means that this matrix M of T looks like you start with these n solutions, and then you put them here as the columns of the matrix. The Wronskian of V1 to Vn is the determinant of the corresponding fundamental solution matrix. Right? So W of T, or if you want to include these functions you're using, W of V1 through Vn of T would be the determinant of this matrix where you put V1 of T, V2 of T, up to Vn of T as the columns. From our linear algebra overview, we know that linear independence of these columns implies that the determinant is not equal to 0 and that the matrix is invertible. So it's worth pointing out that there are many choices of fundamental solution matrix. Infinitely many choices, since there are many choices of fundamental sets of solutions. But the existence of uniqueness theorem tells us that there is only one satisfying that its value at T naught is the n by n identity matrix. If you start with any fundamental solution matrix, then the one which is the identity at time T naught is given by m of t multiplied on the right by m of t naught inverse, right? And we know that the inverse exists because the determinant is not equal to 0. The solution to the initial value problem, where you have V bar prime of t equals A of t times V bar, and initial condition at T naught equals V naught bar is given by V of t equals M of t times M of T naught inverse times V naught bar. So if you have a fundamental solution matrix, then you can solve this initial value problem just by matrix vector multiplication. If the system that you're looking at, dv dt equals A of t v, is obtained from an nth order linear equation, right? So nth derivative of y plus an minus 1 times the n minus 1th derivative of y then this notion of Wronskian coincides with the previous one. Right? So I'll let you check that on your own as a useful exercise. Now, just like that one satisfied Abel's theorem, this one satisfies the Abel-Liouville theorem, right? Named after Niels Heinrich Abel and Joseph Liouville. So the theorem says that if you have V1 to Vn fundamental set of solutions, to the linear equation dv dt equals A of tv, W of t is their Wronskian, and then the trace of the matrix A is defined to be the sum of the elements on its diagonal, then the Wronskian satisfies the homogeneous first order equation dw by dt is equal to the trace of A of t times W. In particular, if A of t is continuous on some interval, then the Wronskian is either always equal to 0 on this interval, or never equal to 0. Okay, we're not going to prove this theorem, although the proof is very similar to the one we did last time for Abel's theorem. You just take the derivative of the fundamental solution matrix with respect to t, think of that one row at a time, and then use properties of determinants. But in any case, what we most care about is this conclusion that as long as you're working with continuous coefficients, then the Wronskian is either always equal to 0 or never equal to 0. Okay, we'll stop there, pick it up from there next time.